Good evening and welcome to this Eyestar clinical value and use of the Eyestar Cataract Suite vision simulation and Zernike analysis tool. My name is Thomas Beutler. I am the product manager for biometry, IOL calculation, and anterior chamber OCT with Haag-Streit. I've been with Haag-Streit for more than 16 years now. Was responsible for basically all the products we have in our portfolio except for the visual fields, and for the last 8 years mainly focusing on biometry and IOL calculation. So tonight we're going to talk about the cataract suite of Eyestar and specifically the vision simulation and Zernike analysis tool of the unit. As said before, please use the Zoom Q&A functionality to ask questions, or also the chat window. We're going to answer questions at the end of the session. And let's just start and have a first look. So why do we need more than just axial length and keratometry for cataract application? Well, the answer is pretty simple. We do have patients which are more informed nowadays. I mean, we have the internet available all around. People are getting information from there. They're getting information from newspapers. So what's available on the market is more in the mind of the patient, and they don't want to just have treatment for the cataract. They also look for spectacle independence. They look for more improved visual outcomes. So multifocality is something they may ask for. And therefore, we need more than just axial length and keratometry. Also, premium implants need more information than just AL and Ks, because if you have a multifocal implant and you have, for example, severe coma, you don't want to have this implant in this patient, because then the performance will not be optimal, and the patient which pays extra for this will be unhappy. That's not good. And last but not least, having more information available on the eye than just axial length and keratometry also enables you as eye care specialist to provide a better basis for the cataract patient to decide on the optimal implant for him or her. So somebody who is actually a candidate for a toric IOL or a multifocal IOL can then make the right decision, also to invest more on his vision to get a better outcome and a more independent life from with respect to its visual acuity. So what does the Eyestar provide you with, and specifically the Cataract Suite, to get you covered? So with the Eyestar, you get a unit that has a comprehensive set of data for any kind of cataract. So independently, if you want to do just a simple standard spherical IOL, or if you go for a toric or a multifocal toric or an EDOF, extended depth of field IOL, you get all the information needed to get the right choice of implant, and then also to get the right calculation for the implant. So you get swept source-based OCT biometry of the entire eye from the cornea to the retina. That was part of a previous webinar here. You also get standard reflective keratometry for best corneal power. You might ask, why do they still do this old technology? We'll have a little recap on this as well. And you get corneal front and back topography, pachymetry, and as part of this tool, you get simulated keratometry, you get zone-based keratometry, you get the Zernike analysis, and you get vision simulation. All of these are going to be focus parts of this talk tonight. Okay. So let's do first a little recap. Why is reflective keratometry still such a crucial part in the decision-making process for the IOL? Sure, one can say if you have a high resolution OCT unit like we do with the Eyestar, you get simulated keratometry from the OCT. That's correct. And these are of high quality. That's also correct. But it's a different way of measuring the corneal curvature. If we compare reflective keratometry to simulated keratometry from the OCT, we have to consider that the baseline information of these two modalities is inherently different. When you look at reflective keratometry, we are fitting a geometrical structure, an ellipsoid, into the reflection points, into the 32 points from the Eyestar. So there we have a direct measurement with the basic information used for keratometry, which is an ellipsoid, which has two meridians, which are 90 degrees to each other. And that's it. If you're looking at simulated keratometry from the OCT topography data, then we first take height information, elevation information, like from a geographic map. So first we have this height curve, elevation information, and from there we then derive keratometry values, simulated keratometries. And in average, they match. They match perfectly fine. But on the individual patients, because they are based on different information bases, they may differ quite a bit. So let's have a quick look, a little bit more detail here. On the left side top, you see the comparison of the Eyestar keratometry to the Lenstar keratometry. Both are reflective keratometries. Both are based on 32 measurement points on a dual zone keratometry measurement. And you can see they match perfectly well. We have a correlation which is almost perfect. And we also see from the Blunt-Altman plot that the individual differences are rather small. So everything is within 0.2 diopters. If we look at the same comparison, the Eyestar simulated K versus the Lenstar keratometry, we again see that in average, they match well. So we have a correlation which is almost perfect, but we can see that the spread in the Blunt-Altman plot is much bigger. And that's what I mean when I say that the individual differences might be bigger if you compare sim case to real case or to reflective keratometry. And that's why we've chosen to also implement reflective keratometry in the Eyestar. So what are the clinical benefits? What are the clinical values you get from the reflective keratometry? They have excellent precision. I mean, you know from years of experience with the Lenstar, and you'll also see this and experience this in the Eyestar, that the reflective keratometry is really, really stable, independent of the patient. We have proven performance. There have been numerous papers that show that these front corneal values are very stable and very accurate and are of big use in the IOL calculation formula. You also get a qualitative tear film assessment. In the Eyestar, you actually get both the qualitative tear film assessment from the reflection points in the video stream, and you can also see direct feedback from the unit on the stability of the tear film in the measurement values itself. And you can use and go ahead with your IOL calculation formula of choice. And also, you don't have to derive new A constants to start with. You just go with what you have, and you immediately will get good results. And you can improve them by the better quality of measurements you get from the swept source OCT from the Eyestar. And that's why we have not only simulated keratometry, but also real reflective keratometry in the Eyestar. Then keratometry is one feature, and it's a crucial feature in biometry, as we all know, because every error in the keratometry is one forwarded to the IOL calculation. But now we need more when we want to opt for not just a standard spherical IOL, but maybe a toric or a multifocal. And there, the Eyestar provides you with additional information. First of all, you get topography. You get the full topography, as you can see on the right-hand side. You get full topography of the front and the back of the cornea. And you also get a feature which is called zone-based keratometry. Now, what's the difference between normal keratometry or simulated keratometry? They both have the same basis, and zone-based keratometry. So first of all, the keratometry has got its inherent limitation that they just have two meridians, a steep and a flat, and they are always 90 degrees to each other. So it's basically based on an ellipsoid. In the zone-based keratometry, you have maximum 4 meridians, 2 steep, 2 flat per zone, and they are completely independent with respect to its orientation and with respect to its power. So if we have a perfect astigmatic case, the zone-based keratometry and the real keratometry will not differ at all. They might be almost equivalent. But as we can see now in some examples, it's very valuable to see asymmetries and also irregularities. So here we have an almost perfect astigmatism. We have a bow tie. It's an against the rule astigmatism. As we can see, it's almost 0 degrees for the steep axis. And we see on the left side the simulated keratometry. And on the right-hand side, we see the zone-based keratometry. So let's have a little zoom up here. What we can see is that we have the 3 zones, the innermost zone, the 3 millimeter zone, which can also be transferred into day vision. Then we have the 5 millimeter zone, the intermediate zone, which might also refer to night vision because that's the pupil size you're focusing at night, 5 to maybe 6 millimeter at the most. And we have the peripheral zone, the 7 millimeter zone. And now we, in this case, where we have really very nice, almost completely symmetrical astigmatism, we see that the simulated K here with the blue for the flat and the red for the steep meridian, and the zone-based keratometry, they match almost perfect. In the center, they are on top of each other. We also see that the 2 lobes are almost identical. And we also see that in the periphery, they are almost in line with the original. Because we have always some asymmetries, we see that for the outermost zone, we have a little discrepancy, but this is not so much of use because the IOL will never cover this area. IOLs are usually having optical zones up to 6 millimeters. And also if you consider the maximum physiologic diameter of the iris, you hardly ever reach a 7 millimeter pupil. But here you could easily go ahead and say, well, that's a good case for a toric implant. We see that the zone-based keratometry, the real keratometry are matching and there's no difference. Another example here to look at, we have a patient with a slightly bent astigmatism. We see that the simulated keratometry is a little bit turned clockwise because of the larger steep area in the lower lobe. And we see that the simulated keratometry for the zones supports this. So we see that we have for the flat meridian still almost 180 degrees. So that's okay. We have steep meridian to the bottom, which is almost 90 degrees to the 2 flat ones. And we see that the upper part is a little bit tilted. And that is what's going to make the result not perfect if you would implant a toric IOL here. Still, we can see it's not so bad in the mid-central zone and up to 5 millimeters. The whole thing is still quite well aligned, at least for the inferior part and for the flat meridian. The top meridian goes a little bit clockwise because of the tilting of the astigmatism. So not a perfect case, but still might be okay to go for a toric, at least in day vision. But you can already see and inform the patient that there might be some limitations due to the topography and the zone-based keratometry here. If we have even further asymmetries, like in this example here, which I would like to have a quick look at, we'll see that now we have in the zones even areas where we just have one steep area and a flat area, and we don't have 4 meridians any longer, but just 2 for flat area and steep area in the periphery, or also in the intermediate zone. So here we can definitely see that if we would still opt for a toric here, that at night vision, there will be some limitations due to the fact that we do have not a perfectly nice astigmatism. We have some asymmetry from superior to inferior, and we also see that the whole thing is bent slightly. This example we will use also later on in the Zernike analysis to have a little closer look on what we get from there. So, as a little summary, what do we get from a clinical perspective here from the zone-based keratometry? We can check for the regularity and symmetry for the astigmatism. We can double check the keratometry, and it's a decision support specifically for toric implants. Shall we go for one, or do we better inform the patient that he or she might not be the perfect candidate for a toric, but might be other solutions to go for? Okay. So now we are facing Zernike analysis. What are we talking about when we talk about Zernike coefficients? Basically, Zernike developed a system where he describes the corneal surface as a combination of coefficients describing different visual aspects. So basically, he shows what kind of visual imperfection leads to loss in contrast in the visual system of the cornea. And this is then described in the Zernike pyramid, which you can see on the right-hand side, small, which you're going to look a little bit more in detail here. We have the Zernike tree here down to the 4th order, and we have so-called low-order aberrations and high-order aberrations. The low-order aberrations, the Zernike coefficient 2, they can be corrected in IOLs or in a glasses prescription. We have piston, we have defocus, and we have the astigmatism, which we can all correct with the standard care we look at. The higher order aberrations, there we have the asymmetries. That's basically the coma. We have the asphericity, and we have second order astigmatism and trefoils here and here. These cannot be corrected by standard means. So if we have high coma, then the patient will always suffer some vision impairment, even if we have a perfect correction of everything in the lower order aberrations, if we correct for the astigmatism or if we correct for the defocus. What we can correct a little is the asphericity, because we all know that some of the implants, they do have negative asphericity and the eye might have positive. And because all the Zernike polynomials are always adding, there we can have some correction to this. So if we look at a Zernike wavefront like here, this topography, that's always a combination of the individual coefficients. So we start with defocus, we add the astigmatism, we add the coma, we add the trefoil, we add the spherical aberration. You can always see on the bottom how this is going to add up. We add the quadrifoils, we add secondary astigmatism, secondary trefoils, and then as we add all these parameters together, we get again the same outcome. So we go back, we see that we first start with just the defocus, then the astigmatism adds, and the further we go down, the more it becomes to the last result, which is basically the topography we see here. So it's not at that at the addition of all the different effects. And we can also have a look at individual effects and explain a patient, well, that's what's happening to your vision if we correct for astigmatism, for example. And this we do in the vision simulation. So let's go back and have a look here, what this means for the patient, because he or she might not really know what's coma or what's the effect of a coma. Here we have now Landolt rings, and you see the effect on the vision of a patient. So defocus, basically just blur. With the oblique or normal astigmatism, with rule or against rule, we have some distortion of the image. So we have a little stretching and also blur. Coma, they have double vision. So we see C is actually double visioned down here, or to the right-hand side if we have horizontal or vertical coma. Trefoil gives these hotspots here, which you can also see here. And we have here the spherical aberration again, second order astigmatism, and the second order trefoil here. Now, let's go back and have a look at the example we just looked at with the bent astigmatism. If you would have just axial length and case, that's what we are stuck with. We have quite a normal axial length, we have quite normal ACD, normal lens thickness, we have a little bit of astigmatism, about 1.5 diopter at 84 degrees. Sounds quite normal. Could be a candidate for low power toric IOL. But what do we see if we go further and look a little bit beyond the curtain? First of all, let's add topography again. And as I said, that's the same example we just looked at with a little bent astigmatism and a little bit of asymmetry top to bottom. And we can already see, we should be a little bit careful here and talk to the patient. Is a toric implant really the choice to go or not? So we see again the bending. We see here the diameter of an implant, that's 5 millimeters here. And we see, okay, there's still quite a good horizontal agreement, but vertically we see the bending. We also see here some asymmetry on the top. Now, if we looked at the zone-based keratometry as we did just beforehand, we already see that at night we might have quite a good result, but at day with a bigger pupil, there might be some limitations because there we have, due to the asymmetries, steep and flat areas, but not a nice astigmatism any longer. So being cautious might be beneficial, but still this might not mean a lot to the patient. There the Zernike decompensation and the vision simulation can kick in and help to explain what happens to the actual patient. With the Zernike decompensation, we also get vision simulation, get individual coefficients, and we can look at them at different pupil sizes. So here, that's the display we have in the Eyestar. We have the coefficients on the right-hand side. We have the values. We have the low order aberrations, which you can turn on and off as total, and the higher order aberrations turn on and off in total. And we have down here the vision simulation. With the Snellen knee, you can also switch to Landolt rings if you want to. And we have the pupil diameter we are looking at. So here in this patient, we can see that the most part of his vision impairment comes from astigmatism, which you can see here with the Zernike polynomial 2.2. We can also see that we do have some coma here. We did have the asymmetry, remember this, and we have a little bit of asphericity down here. So if we now go and say, well, that's what happens if we implant a toric, we can basically just turn off the low order aberrations, correct for the astigmatism, and we immediately see here at the Snellen E the improvement. So that was without the toric, that would be with the toric. But because we don't have a perfect astigmatism, we do have the effects here with the coma. We see that we still suffer some loss in visual performance, and we have some double images because of the asymmetry of the cornea. And this can be shown to the patient. So that's at the 6 millimeter pupil, that's basically at night. Now, if we go and say at day, that's what you can experience then, we see that the toric implant here helps a lot. We get almost perfect correction because of the smaller pupil. And we can also see that now the coma values did decrease dramatically because we're looking at the smaller area of the cornea. And there the asymmetry is much smaller. So we could basically explain, if you go for a toric at day, it will work perfectly fine. At night, you'll have some impairments. So we have here again the full story, no correction with a toric at night and with a toric at day. So in this example, we see nicely that having all these tools at hand, we're having keratometry, biometry, having zone-based simulated keratometry, and having Zernike analysis and vision simulation allows us to provide the user with improved information to get the right decision on the implant to get the best visual outcome. So that was all in presentation style. What I would like to add quickly here is a quick session on a patient on a real unit. So I'm going to show you quick live hands-on here on the Eyestar. So we are now connected to an Eyestar unit. You can see here, patient, that's iSuite, which we have on all the units we are using with the patient manager, the cataract switch to acquire data and the IOL calculation. Here, I just selected the patient. Let's have a look at it. I load it on the unit itself, so that's live. The unit is actually sitting in the office. Due to Corona, I'm hosting this session from my home office. And we have here a patient where we can see, looks pretty cool, at least on the left eye. Nice astigmatic case, some asymmetry here, but the lobes are pretty symmetrical. So let's have a little more detailed look at this. So we open up the topography, and we have here now the display with zone-based keratometry on top. We still see that we have nice agreement for central and the intermediate zone here. We also have a nice agreement on the flat meridian. So this might be a good candidate. We see that we have some asymmetry here, horizontal. Vertically, there's less asymmetry. Now, if we go to Zernike, we have again the vision simulation down here, Snellen E. I can switch here also to another display, Snellen chart E with little edges here. So that's how it would look, perfect case. Then we have the Landvold rings, and we have again the Snellen set. So you can select whatever you prefer. I go for the E. We have here again the polynomials. We have here the root mean square of the lower order operations and the higher order operations. Now, you might also say, well, there are rules of thumb for when shall I go for a premium implant or not. Usually, this rule of thumb is if you have higher order operations more than 0.4 microns, you should not go for a premium, which is right. That's a good rule of thumb. But as I said, these Zernike polynomials, they are always additive. So it might be that if you correct for something, that something else is suffering. So for example, here, if we say, well, we put in, let's say, an IOL that has got some negative asphericity to compensate for this 0.2 positive. What we could see if we just do this, it doesn't really help a lot. So we have now an even worse situation here on top of the Snellen E, and we lose again contrast. So it's not always just one thing you look at. You always have to look at the complete symphony of the coefficients. So again, we did look at this patient. Is it a candidate for a toric or not? Now, if we want to look at the toric, we say, well, what would happen if we implant a toric IOL here? So we correct for the lower order operations here, just click on LOA button, and we immediately see, that's quite an improvement at the 6 millimeter pupil. So at night vision, that's what we can expect without the toric, with a toric. Now, if we go back to topography, we already see we have asymmetry here. And we also see this here in the Zernike tree, because we have here the sorry, the horizontal coma, which is quite big, and that's the asymmetry we also see here, and that's what makes now one of the biggest effects here at night vision. Still, we could say we go for an aspheric implant and correct here a little bit. That would add a little bit. We can show this all to the patient, what would happening if we can have this, an aspheric implant, if we would do a toric. Now let's just look for the toric, 6 millimeter pupil night. I can now say, well, let's have a look how it would be at day. And I switch just the diameter of the pupil on the fly and then immediately get the feedback here. So that's with a toric at day. That's without the toric. And you can show nicely the user, whoa, that's quite an impact. That's much better than before. So a toric might be a good choice here. So with this tool, you can interactively educate the patient to then go for the right decision to achieve the best performance for his or her vision. On the unit or also on a viewing station, you've seen all this is on Eyessuite. I connected here now to an Eyestar unit, but I could also do this on a viewing station of Eyessuite and have the exact same experience without the acquisition tool, because then it would be just a viewer, but it is also having the same tools to work on. Okay. So to sum it up, the Eyestar provides you with a real topographer with 7.5 millimeter coverage in the cataract suite. In the soon to come anterior chamber suite, we will cover even up to 12 millimeter for topography and up to 18 millimeter for imaging. We have the zone-based keratometry for reassurance and double checking of the reflective keratometry. We have then a double check and certainty that everything is right. And we have the Zernike wavefront to educate the patient what effect is based on what vision imperfection of the cornea, and therefore the right choice of implant can be made. Okay, so that's a broad overview on what you can do and what you get from the zone-based keratometry, from the Zernike analysis and the vision simulation. We've seen this, it's an interactive way to communicate with the patient to get him to the right decision in the end to get the perfect outcome. Okay, so let's have a quick look at the Q&A section. I have one question there. Do you also offer total wavefront aberration map of the cornea front and back surface? So that's basically a question here in the Eyestar. So I'll quickly go back and connect to the Eyestar again. In the overview here, we have the front and the back independently. Currently, we are not offering a total power map yet, but that's going to come. Why did we do this right now immediately? We could easily add front and back together and provide information on this, but then it would be just a combination of the two information parts. And it might not be the refractive result you would get. Therefore, we are right now assessing more data to then get a combined information piece that really refers to the refractive power of the cornea and not just a combination, a vector combination of front and back. And that's why it's not yet in there. And I've seen there was also a question in the Q&A. In case of a big difference between the reflective keratometry and the sim case, which of the measurements would you recommend to use for the IOL calculation? Well, it really depends on what you would go for. I mean, we can go back here and have a look at this case here. We have simulated keratometry with axis of 84 degrees, and we have the reflective keratometry at 80 degrees, 2 diopter astigmatism on the reflective keratometry, and the topography, it was a little bit more, 2.5, but in general, they are matching quite well. If we go again to the topography, we see the reason why the sim case a little bit more to the left. That's basically due to the fact that the lower part here is a little bit stronger and rotates the whole thing a little bit clockwise. That's why we have 84 degrees in the sim case and 80 degrees in the reflective keratometry. Reflective keratometry just looks at the two rings at 1.65 and 2.3 millimeters. So that's a very limited area we are looking at. The simulated keratometry looks at the whole cornea in more detail because it's based on the elevation data. That's why you have some differences. What to rely on if you have big differences? Still for the IOL calculation, the power, I would most of the time go for the keratometry and the axis, depending on where you're going to go. If you have big discrepancies, you might anyway just opt for a spherical implant, because then there might be other reasons why we have such big differences. That's usually due to big differences or big asymmetries in the astigmatism. And then it might be not the best option to go for a premium implant. But keratometry itself is still quite stable and independent of the measurement quality itself. Okay, then there are more questions. Yes, there's a one side mark. Dr. Hill said he would not use sim case for the IOL calculation. That's correct. And that's what basically I just said right now again. Sim case are not of the same quality. And you have seen this in the little comparison where we did have a look at. That if we look at simulated keratometry, that these are spreading quite a bit on the individual patient because they are more affected on asymmetry effects of the astigmatism. So if you have a real asymmetric astigmatism, then this has quite an effect on the simulated keratometry. This effect is not so much on the reflective keratometry, and therefore I would always go for reflective case, maybe adjust the axis depending on what you see in the topography and the sim case. I quickly look if we have more questions. Somebody's asking if you could quickly show the option of lens tilt. Sure, I can quickly go back and show you also the lens tilt here. So here we have the lens tilt, and there we see the outcome. We have here the infrared image where we see the plane of the maximum lens tilt. Here it's a crystalline lens that's usually close to the horizontal, as we would expect. And we see then here the OCTB scan. This is a cut from here to here. So it's always with the dot here that shows the start of the cut. And we see then the lens tilt from the visual axis to the tilt of the lens. That's a crystalline lens here. And we could also have a look at something else. So quickly switch the patient here. As you can see, we are doing this all live. And here we have the same also for an implant, for a pseudophakic patient. Lens tilt again. That's a cut from temporal to nasal. And you see here the cut orientation. You see the IOL. the lens tilt here again in the overview. I hope this also did help and answer the question. Let's have a look. There are no more questions in the chat section. In the Q&A section, we also have no more questions. I'll wait a few more seconds. So if there's something you would like to ask, feel free to join us and I'll try to give a reply. There's one question. Do you plan to introduce calipers for the AC suite? Yes. The AC suite is going to feature different parts. One part is going to be a topography part, as said before. It's going to have features like timeline comparison. It's also going to feature in the full step features for screening for keratoconus and so forth. It's also going to have chamber angle analysis feature, and it's going to have imaging feature that allows some measurements, either just pixel-wise or comparative measurements, but also real measurements in millimeters, depending on where you're measuring in the OCT image. But that's actually planned, but that's soon to come. So currently we have the Cataract Suite. That's what I did show you here in the live stream, and the IC Suite is soon to come. Okay, so there are no more questions. I would like to thank you very much for your participation in this webinar. Feel free to look at this also on our YouTube channel and from our webpage. It's going to be online soon. We have more webinars this week. We have a webinar on IOL calculation for toric IOL tomorrow for Lenstar and Eyestar. We're going to have first experience from 2 clinicians later on this week, and also more information on more topics in the coming week. So please feel free to join us again and see you soon in this channel. Thank you very much and have a good evening.